Now let's begin the final topic of 7.2 trigonometric integrals. We'll talk about reduction formula. Please be warned, this is not for everybody. This is an optional topic. So if you get lost, that's okay. And if you do understand everything, great. Let's begin with a motivational example. And I think it's right here. Example 8, I think. Is it example 9? Example 8. Find the antiderivative of secant to the third power. And before that, tangent to the third power was not difficult at all, but this one is also a kind of reduction formula too. How do you calculate the antiderivative of tangent cubed? And we can decompose tangent cubed into tangent times tangent squared, and tangent squared can be rewritten as secant squared minus 1. And this is typical trick, isn't it? Tangent squared and secant squared, sine squared and cosine squared, cotangent squared and cosecant squared can be interchanged, and this is kind of typical thing. So rewrite tangent squared part into secant squared minus 1 and break up the parentheses. What do we have? Tangent times secant squared. That part, the secant squared part, has second power, that's even power, so you can use y substitution, y as tangent, and then everything works out fine. Consequently, we have a power function of tangent, so 1/2 tangent to the second power, as you can see here. Right hand side, it is just antiderivative of tangent function, and it can be rewritten as log of secant of x. And how it is, well, that's something we already covered in calculus 1. Tangent can be rewritten as sine over cosine, and then u substitution as u equal to cosine, and everything will work out fine. This is actually one of the easier one, even though there are some skips, some steps skipped here, some significant steps hidden between the second and third line. Next example, example 8, is pretty much outrageous as a matter of fact. Well, we can do something similar, and the starting point is actually the same. We do a decomposition as before. Secant to the third power can be written as secant times secant squared, like this. Secant of x, u, and dv is secant squared x dx. And use integration by part. U becomes du by taking the derivative, secant times tangent. dv becomes v by taking antiderivative, we have tangent. So putting everything into the integration by part formula, uv secant times tangent, and then u prime v, or v du, and we have secant times tangent squared dx. Almost there. Tangent squared is interchangeable, so we can change it into secant squared minus 1, break up the parentheses when we have secant cubed, and then secant of x there. Wait a minute, we started off with secant cube and we got secant cube again, and looks like we are nowhere, but as a matter of fact we are somewhere, because this is minus secant to the cubic power. So if I flip it over to the left hand side, and left hand side will be 2 secant cubed, and then this middle term, middle integral, will disappear. Dividing everything by 2, we're going to get, well, something like this. 1/2 of secant times tangent, and then 1/2 of the antiderivative of this secant of x. Is it a little bit complicated? Well, we're going to deal with a little bit more general kind of computation, and we're going to do that in more detail with the Mathematica notebook here. And the very last subsection here is the reduction formulae, and we have these 6 formulae. As a matter of fact, there are more reduction formulae, to tell the truth. If you go over to internet and then go to, well, anything, and then type in any web browser or web search engine, it's taking too long. Okay, never mind. Let's go back to my Mathematica notebook here. And I de-emphasize these in gray because this is not for everybody. This is for optional topic. And here it is one. Sine of to the nth power can be rewritten kind of like this. And the left-hand side, the first term is pretty much all set. Right-hand side, we have sine of n minus second power here. So the integral, this original integral, became a little bit simpler integral. For example, if you begin with sine to the 10th power, and this reduction formula will give you integral of sine to the 8th power. Do it again, and you're going to get the reduction integral of sine of 6th power. And apply the reduction formula again, then you're going to get the integral of sine of 4th power, and so on. And eventually, you're going to come down to manageable integral, and that's basically it. And cosine to the nth power, again, the same deal. We have this first term pretty much set, and right-hand side, in the second part, we have n minus second power, so we got a reduction. Tangent, pretty much the same, reduction by order of 2, and secant, the same, reduction by order of 2, cotangent, the same, reduction by order of 2, and cosecant, again the same, reduction by order of 2. The easiest among these is actually tangent and secant examples, so let's talk about these. And here are the derivations. The very first one is for tangent. Tangent to the nth power can be decomposed into tangent to the n minus second power times tangent squared. It's a this is pretty much the same as the example we did in class, with example we did in textbook. Just a little bit more generalized form. And this tangent squared can be rewritten as secant squared minus 1 by the Pythagorean identity. Break up the parenthesis, and what we have? We have first integral given by tangent to the certain power times secant squared. And secant squared, that makes our life much easier because that's going to be absorbed by dy if I take y as tangent. And this one, we have a little bit simpler integral, tangent to the n minus second power. How about the first integral? Because of the secant squared part, this can be considered as a power function of tangent of x. So antiderivative is just power rule. 1 over n minus 1 tangent to the n minus first power. And then we have antiderivative of tangents to the n minus second power. So this is a reduction. So for example, if I start from tangent to the 50th power, then apply this reduction formula, you're going to get the integral of tangent to the 48th power. Apply it again, we're going to get tangent to the 46th power, and over again, we're going to get something. Of course, that's prohibitively complicated for humans, but for computers, not much a big deal. Okay, how about the next one? Believe it or not, this is the second easiest of all these reduction formulae. Secant to the nth power can be decomposed into secant to the n minus second power times secant squared. And decomposing into something squared, that's pretty typical here. And then we can apply the integration by part. U is secant to the n minus second power. V prime as secant squared of x. Let's calculate u prime by brute force computation, and by power rule we get n minus 2 secant to the n minus third power, and then by chain rule you have to multiply the derivative of the inside, derivative of secant function, secant times tangent. You can simplify this because we have another secant function. So this is n minus 2 times secant to the n minus second power times tangent of x. How about v? V prime is secant squared, so its antiderivative is tangent of x, and that's the only easy component of this problem. So if I put everything to the integration by part formula, and we're going to get the second line here, u times v, so secant to the n minus second power times tangent will be right here. Okay, that's all set. And then minus the integral of u prime v, and u prime, this one, times v, that's tangent of x. So if we do a little bit of simplification, this tangent and that tangent will become tangent squared, and then secant to the n minus second power, we're going to get n minus second power, and we're going to end up with a second line here. Okay, please remember all these, the entire underlying theme of this section 7.2 must be the Pythagorean formula actually. Sine squared plus cosine squared is 1. Tangent squared plus 1 is secant squared. Cotangent squared plus 1 is cosecant squared. Kind of like that. So tangent squared is secant squared minus 1. So breaking up the parentheses, this is what you get. Secant to the nth power and the secant to the n minus second power. The first term is completely set, and the second one is secant to the nth power again, the same as the original one, so we can flip it over to the left hand side. And the final one is a reduced integral. Instead of nth power, we get n minus second power. So if I flip this middle part to the other side, you're going to get something like this. Oops. Equals to that. Okay, that's where we start. And then we're going to flip this one to the other side. So add n minus 2 times this integral to both sides of the equality. Then right hand side it will be just gone. And left hand side adding n minus 1 plus 1. I'm going to get n minus, adding 1 plus n minus 2. I'm going to get n minus 1 times that integral. Now everything is all set. Divide everything by n minus 1 and I'm going to get this integral we wanted all along. And the right hand side I'll have this n minus 1 in the denominator, this and that. That's how we get the final reduction formula. And I don't need this part anymore, and I don't need this part anymore either. And here is the full, concise but full derivation. The other formulae are pretty much the same in the level of depth. Cotangent and cosecant is pretty much parallel with tangent and secant formula, except for some negative signs, and there you go. And for sine and cosine, a little bit more complicated in a sense that you have to combine these. It goes kind of like this: decomposition, and then integration by part, and so on and so forth. Detail is left to the students, and if you are really not understanding any of these, please do not get too mad at yourself, because this is an optional topic, and I have never written any reduction formula problem in Calculus 2 exams ever since actually I started teaching in college level in 1994, and I've never written those kind of problems, and I'm not about to start now, so this is going to be an optional topic. Okay, that concludes section 7.2.